thank you so much for joining us. Thank you so much for making the time to join EMQ's webinar. We really appreciate you making the time, whether it is in your morning, your afternoon, or your evening. We're seeing a few more folks coming into the webinar. Welcome. Thank you. This is EMQ's webinar. So my name is Keen Chan. I am with EMQ's marketing team. And today we're very excited to talk to you about vehicle data. And specifically, we are excited to talk to you about using tech like MQTT and vehicle-to-cloud platform to manage your connected car data. And we're very, very fortunate to have two experts, vehicle software experts, to talk to you about this subject. We have Jaylin Yu. He is the Solution VP at EMQ. And then we have Liu Yixuan. He is the Connected Vehicle Product Specialist at Carlinx. Carlinx is EMQ's company partner at the automotive sector. So both of them will give a presentation, and then we will open to Q&A. So look forward to all of that. And before we start, just a couple of housekeeping notes. First, you can submit your question anytime during the session. You should be able to see a Q&A tab below your screen. You can type your question anytime, and we will address all of them in our Q&A session. And secondly, we will launch a poll at the end of the session. It'll help us greatly to know what kind of topic and subject you would like us to discuss in the future session. So do help us out to fill out the poll. And lastly, if you want to contact us, the best way is always to fill out a contact form. That way we know your specific needs and we can send the right support your way. And with that being said, I will hand the mic over to Liu. He will talk to you about vehicle to cloud and super data bus. All over to you, Liu.
Okay, thank you. Please wait for a moment. I will share my screen.
Of course.
Okay. So good morning and afternoon and good night to the colleagues online. This is Adam from Carlinx Technology. I'm honored to give you guys a presentation today. And so the topic for today's presentation is super data bus for connecting cars and cloud. So let's start with the first part, the introduction for Carlinx Technology. Carlinx Technology is headquartered in Hangzhou with subsidiaries in Shanghai, Wuhan, and Gothenburg. We have more than 400 employees with 90% of R&D. Carlinx Technology's business areas covers the vehicle cloud platform, AI cockpit, large model, and data commercialization, vehicle and cockpit integration test. We have long-term cooperation and mass production project experience with Geely, Lynk & Co., Volvo, Lotus, Smart, and Dongfeng. During the process of project delivery, we adhere to the user-centered approach, explores cutting-edge automotive electronic software technology, helps the intelligent upgrading of the automobile industry. As the leading service provider in intelligent connectivity industry, Carlinx Technology has accessed and independently operated and maintained more than 500,000 overseas vehicles. With global operation and maintenance provided by the team in Gothenburg, our platform covers EU, North America, Middle East, and the Asia market. Carlinx Technology focuses on the overall arrangement of vehicle and cloud integration strategy with continuous innovation on cloud, vehicle, pipeline between the cloud and vehicle. By standardizing software technology, we promote efficient collaboration of service and data between vehicle and cloud, improving the automotive intelligence and the user experience. Next, let's move on to the key point of today's presentation, part 2, the hyperflow. Carlinx Technology focuses on the overall arrangement of vehicle cloud integration strategy with continuous innovation on cloud, vehicle, pipeline between the cloud and the vehicle. By standardizing the software technology, we promote efficient collaboration of service and data between vehicle and cloud, improving the automotive intelligence and the user experience. From the vehicle side, By enhancing the edge computing capabilities, we help OEM to build an intelligent AI cockpit, enhancing the in-car experience and the interaction. From the pipeline side, we devote ourselves to build a new vehicle cloud integration base, forming an efficient and stable vehicle cloud highway to ensure low delay and high reliability of data transmission. From cloud side, we develop a vertical industry model and a big data platform with data-driven and low-code at its core to maximize the business of value data. Next, I will introduce the key topic, Hyperflow, the super data bus between vehicle and cloud to you guys. With the rapid development of AI and intelligent network technology, vehicle functions and the product definitions are becoming increasingly complex. The number of associated ECUs is constantly increasing. The scope of function dependency on data is also significantly expanded at the same time. However, the different data need to be collected through a variety of pipelines, resulting in dispersed data assets. The lack of cooperation between transmission pipelines puts forward higher requirements for the flexibility and the intelligence of data collection. In this context, the importance of the vehicle cloud integration base is particularly prominent. Based on this unified infrastructure and data platform, we can not only achieve efficient data collection and integration, but also provide AI-driven scenario-based services and immersive experiences for customers. Meanwhile, we empower automotive enterprise by connecting end-to-end data links, helping transformation from passive services to active interactive services. Finally, a new business model driven by data is formed. However, in the process of realizing the vehicle cloud integration, there are still bottlenecks and challenges. The data collection of OEM now still relies on the traditional TSP channel. On the original data is without pre-processing and compression during the collection process. Not only need to consume a lot of mobile traffic for data upload, but also need the cloud to spend a lot of cloud resources for secondary cleaning and data in the lake. Secondly, due to the service attributes of traditional TSP channels, the service priority of traditional vehicle control and connectivity is higher than that of alarm monitoring diagnosis services, and the timeliness of data is poor. When facing network scenarios, traditional TCP technology will cause data delay loss. Nowadays, OEMs generally have multiple domains at the car end, such as the cockpit domain and the auto-driving domain. Data involving multiple domains cannot be exchanged locally in the vehicle or rely on the cloud for data integration. However, the data collection strategy is limited by the OTA of the car terminal software, which cannot realize the flexible rule configuration and policy update. From cloud side, traditional data clusters cannot meet the high concurrency and the high throughput architecture of the AI area, which requires a lot of cloud resources to enter the lake. Due to business and management requirements, most of the OEMs use private technology and protocols for internal modules. The use of a large number of non-open source technologies has also led to rising custom development and operation costs. Next, let's move on to the Hyperflow solution. During the process of achieving the vehicle cloud integration, we need to firstly understand its approach and the key technologies it relies on. At the car end, the creation and update of rules and models need to support real-time regulation of collection and calculation rules. During the operation of vehicle, a large number of data generated at the vehicle end. This data need to be streaming and batch uploaded based on the priority of the actual business. Before uploading the data, the relevant data needs to be encrypted and compressed according to the requirements of OEM, so as to ensure the security of the network between the car and the cloud, achieving the reliable data transmission. On cloud side, infrastructure needs to support increasing volume of data and the concurrent access from the car side. Through the data cleaning, cloud services filters the service data to the algorithm model. After model training and updating, it is necessary to support the cloud flexible configuration and update new collection rules and models to send it to the vehicle side. to forming a closed loop for model training. Hyperflow is the platform solution based on the concept of next-generation vehicle and cloud integration, defined by Carlinx technology with deep cooperation from EMQ side. Carlinx technology is mainly responsible for the definition of cloud management platform, including the task configuration and deployment of data collection, maintenance of algorithm rules, vehicle data access, and the data dashboard. EMQ mainly responsible for vehicle protocol adaptation, the real-time rule calculation, collection task scheduling, and the data upload. Based on the Hyperflow solution, we can help OEMs achieve substantial cost reduction and the efficiency with the combination of the mass production experience in the OEMs. Our solution is adapted to the mainstream OS, hardware architecture, and the resource allocation, saving 50% of the adaptation and the access cost of the OEM. Through EMQ's powerful stream processing engine capability, this can reduce the computing power consumption in car by 50%, while achieving the lightweight stream processing calculation at the same time. Based on the application of high compression algorithm, we reduce the occupancy of internal memory by 75% on the vehicle side, and they effectively reduce the mobile traffic consumption by 90%. The cluster architecture based on EMQ saves the gateway costs and avoid the resource consumptions of secondary data cleaning after the data enters the lake. Hyperflow solution is implemented based on standards, open standards, and open source protocols to ensure 100% autonomous and controllable. Next, let's talk about the application scenario of Hyperflow in flexible data collection. For example, the vehicle side monitors the key signals of the power domain of the body area in real time. When edge computing identifies abnormal events such as rapid acceleration, frequent braking, or sharp turning, Hyperflow will report an early warning to the OEM system. For another example, in the scenario of after-sales diagnosis analysis, OEM generally collected CAN signals for the whole vehicle. Based on the ability of the Hyperflow, all vehicle signals can be compressed locally. After identifying the scene events like monitoring force, the full disk data of a period of time before and after the event will be uploaded from the vehicle side to cloud. Let's move on to the application scenario of Hyperflow in intelligent cockpit. While access to sensors in the car, Hyperflow can combine sensor data with Edge AI, real-time adjustments of cockpit temperature, humidity, and the fragrance to achieve intelligent adjustments of driving atmosphere or the driving mode. Meanwhile, with access to smart wearable devices, such as the smart bracelet and the smart watches, to realize the cockpit control and the driver physiological monitoring. The concept of digital twins should be heard. To achieve the true digital twin, there are extremely high requirements for data collection and edge computing. On the basis of realizing the basic data collection, Hyperflow provides the cloud channel of the algorithm module update. The algorithm module runs at the vehicle site and deduce based on real-time in-car data. Based on the inference results of the vehicle terminal algorithm, if there is any differences between the inference results and the user's actual results, Hyperflow will upload the data related to the algorithm inference and normalize to the cloud so as to close the loop cloud model training. In the relevant scenarios of remote diagnosis, the current main solution of OEM still stays in the mode of issuing the diagnostic commands from the cloud side and then upload the relevant diagnostic data by vehicle side. Through the capabilities of the Hyperflow, we can identify the fault events at vehicle sites through the edge computing. When detecting such kind of events, we will push the related alarms to the OEM after-sales department according to different fault types. Based on the reported diagnostic data, the relevant staff of the after-sales department can contact the customer to provide proactive services, help the customer to solve the problem, turning the old user looking for OEM to solve and complain about the vehicle breakdown issues into the OEM proactively contact the customers to solve the problem after identifying the faults. Finally, such kind of way can reduce the user's complaints and improving the user's car experience. For vehicle safety scenarios, when a collision occurs in the process of using the vehicle, Hyperflow can identify collision scenarios such as the stretches and the rear-end collision based on the local model capabilities on vehicle side. Different alarm contents are provided to the cloud based on the severity of the accident, so that OEM can formulate different services strategies to serve the users. For the scenario of new energy battery monitoring, the feed model can carry out full screen monitoring for scenarios such as agent and abnormal dormancy, which is convenient for OEM to obtain first-hand and the full volume key indicators. Based on the Hyperflow solution, Carlinx technology is committed to build a super data bus between vehicle and the cloud, helping OEMs to achieve the cabin intelligence while reducing cost and increasing efficiency at the same time. Through a unified vehicle cloud communication protocol, we establish a lightweight, high-speed data channel independent of the existing telematics channel. While meeting the daily business needs of OEMs, Hyperflow helps OEM to create a new user-centered active service system. So here is the ways to contact us. You can contact us through this email or fill in the information with this QR code. That's all from my side. Thank you guys for today's time.
Yeah, and next we will have Jalen Yu from EMQ to talk to you about software-defined vehicle revolution. Jalen, you can feel free to share your screen and open your camera whenever you are ready.
Okay, sure. Thanks, Yishan, for your detailed presentation. Now, I will follow your topic to explain what is software-defined vehicle and why this matters, and why we are seeing the whole industry is experiencing a revolution. Okay, so as you might have known, the automotive industry this revolution has evolved from just focusing on the electrification to embracing the intelligence. Yeah, like interpret the data, those data collected from the edge device and collected from the in or internal vehicles, then to the cloud. At the heart of this transformation is a software-defined vehicle. Yeah, as I mentioned here, state here. An SDV, which is software vehicle, has a different value proposition than that of a traditional vehicle. With that being said, the car you are driving every day, that car is no longer being finalized at the very moment it was manufactured. The passenger and the driving experience are no longer being determined by mechanical or electrical systems, because the software capabilities is continually improved during the vehicle's whole life cycle, from the time it was manufactured and handed over by each drivers, and at the end of its life cycles. Yeah, for example, now we have a lot of a cloud-based service, a location-based service, and you can navigating on your smartphone to see the real-time status of your vehicles, even to communicate with your vehicles. Yeah, it's not even to mention that a lot of previous existed smart intelligent application like a digital cockpit. Yeah, so and along with the assisted driving, and which has shifted the industry's focus away from internal combustion engines and mechanical engineering. The integration of advancements from computer science and information technology into automotive sectors has given rise to the features like ADAS here, yeah, and the digital cockpit. And these innovations ensures that vehicles' driving experience and functionalities are not fixed at the moment, at the point of manufacture, but can dynamically enhanced to meet users' needs. So you can have your own driving experience with your own vehicles, and it is totally different from others. And with the process through the ongoing software updates during the whole vehicle lifespan. Yeah. So and to ingest the software into the hardware of your vehicle is not a fresh thing since the past decades. Yeah. Even 50 years ago, we see the first generation of ABS features, then airbag, then ASR, then we can at the 90s era, we see infotainment systems. And now, yeah, we finally are experiencing an exciting software world. But under the hood, what is really going on? So just like what we have been through on IT on the cloud world, or we see that our IT architecture was distributed, then got a centralized cloud service, then we got different tiers of service from edge, from end device to the edge computing and to the cloud. And in your vehicles, you can imagine there are different computing domains. Yeah. So here is a picture from Bosch, and they have shown us a clear roadmap of how to adapt to the new SDV world. So in the past days, the ECU, which is the electro computing unit in your vehicles, they are communicate with each other via different signal-based methodologies. Like you might have on your at your high school class, the signal are drops and rise, and the different wave format of your signal indicates a different state of that ECUs. Yeah. With after we have moving forward to the software world, now high bandwidth Ethernet has been adopted into the vehicles. Yeah, the ECUs and the multiple ECU now combusted each other into a high tier of SoC parts, which has a much higher computing power, can sustain much complicated applications. Software-defined vehicles or service-oriented architecture, which is a way of designing your software for your vehicles, where the participating components provide and consume service over predefined protocols over a network. So, which is thanks to the next generation of Ethernet technology being widely used in the vehicles. It gives us a great advantage, like we can decouple the different ECUs. We can have to combine which was distributed the computation power was distributed. Now they are concentrated, and which can allocate it and we can make full use of them. And with concentrated of computation power and vehicle data, now we can provide a higher tier of interoperabilities and improve our service reusabilities. So we are no longer stick with like CAN bus, FlexRay, and Lean bus. Now between those major ECU or DCU or VCU is is the Ethernet cables, which is commonly seen at modern technology. So we're moving from the signal-based communication to the service-based communication. So in the past histories, yeah, like 50 years ago, your vehicles or our cars is basically a huge mechanical toys. Yeah, you got a lot of different ECUs which are only responsible for specific features like open the door or adjusting the your engines. Yeah. And then we got a domain controller. a domain controller might be, for example, your body controller module. Body control module is responsible for your driving experience, to provide you the metrics of your tires, your engines, and provide you HUD to assist while you're driving. So after that, we're moving forward to the 21st centuries. Now we got multiple domain controllers. Each domain controller has a series special ECUs which is linked with each other and decoupled with other domains, which is a way to isolate your domain functionalities from other domains, like isolate your powertrain from your cockpit. Yeah, because they requires different level of safety standards. So as a picture shown here, this is the most commonly seen architecture of modern vehicles. But we are still moving forward. Now we're seeing the different domain controllers are even more concentrated. We are seeing a vehicle computer which is capable of high performance computing now emerges in your vehicles. Yeah, we see the NVIDIA Rings series, which is commonly used in your vehicles for ADAS features, and we see a lot of Qualcomm 8295 series, which is used for far more sophisticated features in your cockpit. Yeah, those chips was not designed for vehicle in the very moment at it birth, but it's this revolution to combine the most advanced technology from IT world, from the semiconductor world to the vehicles. Yeah. Now, so this is the most advanced architecture, EE architecture of vehicles we could see at modern OEMs. Yeah, each vehicle might have one or two vehicle computers. Each vehicle computers is responsible for one specific front part of your vehicle, and another one is responsible for the rest part of vehicles. Yeah. And they communicate with each other at a very high pace of data rate. Okay, now you see we got a lot of things going on in your vehicles. We are moving from the domain controller to the zonal controllers, from a vintage car to high-end electrical car with high performance computer inside. So our experience gonna be far more different from last centuries. Yeah. So now we can dive into the technical part or technical space to see what is the driving power behind all this, because the vehicle actually it's like a miracle. Suddenly a lot of new technology emerging on, and we are seeing electric vehicle now is everywhere. So why is this happening? So actually, behind this, I would like to mention about AutoZar standards and open source world. So in the previous days, the OEMs or automotive manufacturers, they are pretty isolated world. Yeah. So in the previous days, the OEMs build their cars by integrating the technology from different tiers of vendors, like Vector, EB, or ETAS, and then design their vehicles by the tool chain I show here. They write the XML files to configure the different signals of each ECUs and how they communicate with each other. Then they generate the data, generate the code, and generate the firmwares to flash them into the SOC ECUs, and then combine those ECU parts to the vehicles, and then doing some more tests, and then now the vehicle is functioning. Yeah. But after we put more and more software into vehicles, what I just mentioned was the AutoSAR CP standards. But after we evolve into the vehicle with more software inside, now it's new standards of AutoSAR emerges, which is AutoSAR AP, which means called here adaptive auto applications. You can see this is far more complicated than the CP parts, because we got more things going on. We got more data is transmitted, and it's just like a higher end data centers in the cloud, but in a higher safety standards. So each part of them basically are actually just a POSIX program, and each POSIX program they got their own threads. They got their own. They were isolated from each other to run in their own space. Okay. The story is now we got new standards to deal with the software. However, the developing power of automotive manufacturers is not that advanced. They cannot adapt it to compete with the higher pace of development development speed from the IT world. So here is where this is where open source gonna shine. So open source provides a huge database and huge technology base for the developers and for traditional manufacturers to take advantage on. So they adapt to open source technologies to exclude those outdated tool chain from the previous tier one vendors like listed here. So a lot of open source technology now is being widely deployed into the AutoSAR world. You can see now AutoSAR is introducing the DDS protocol into the vehicle world, and also like MQTT, which is now is widely used in AutoSAR standards and widely used in the vehicle cloud communications. Now, what I want to mention is another widely used open source standard, which is Parquet. So in the previous days, the data format in the vehicle is quite closed. Each vendors has their own data format. You cannot share the data file with other vendors toolchain. So basically, once you bought the toolchain from like Victor, you cannot now you just cannot be allied with like EBO with other competitors like Bosch. So and their toolchains is insanely expensive. But nowadays we got the open source powers. So the Parkway now is widely used, especially in ADAS, in auto driving, autopiloting technology parts. So Parkway is data format to combining those different data formats, different signals into one unified format. Now, and it shares a huge open source community supports, and we can use the data tools to interpret, to compress, to decode, to encode the data with for free tools. So now you know what is going on in the automotive world. Now, but the thing is not like it's not like as smooth as we think before. So because the data volume and the data type now is keep rising, so we got different data source like camera, lidar, radar, GPS. They produce different kinds of data like video string, point cloud, a binary data struct, and text string, and they and especially the video data is now is being produced at a very high pace every day in your vehicles, especially for ADAS features. They even got a different data frequency. They got different protocols. So, but imagine it: if you wanted to build successful features like ADAS feature or digital cockpit feature for your vehicles. It's pretty hard for you to combining those data in one domain to provide a higher interoperability for you to deal with those data. Yeah. And now your vehicle is more and more, even more complicated than before, and you need to deal far more data in one SoC than before. So it raises a huge challenge to previous softwares, which is developed for the vehicles. So now this is why I think we're gonna bring a new ideology to the vehicle here. So we got a multi-domain architecture here, and we need to combine those data together. So imagine this. This is just like we need to deal with a different service, a cloud service. We need to make all this cloud service can exchange data in higher efficiency. But so what we do in the cloud, we put a broker here. Yeah, we put a data bus here. The data bus could exchange data, share data without extra cost. Yeah. So the upper part here is what we deal with the data spaghetti ECUs on cloud. So same problem here in vehicles. We got more and more domains, and the data volume raise up. So and the different ECUs need to communicate with each other. So we need to add a middleware in between your operating system and your application ecosystems. So the middleware provides you the atomic service for you to exchange data. So this is one part. Another part is as we keep talking about the software here. So we know, the software now constitutes a large share of vehicle development cost compared to the hardwares. So the software cost rises from 34% to 75%. Yeah. And in the previous days, we all know a development model of automotive world, which is ASPICE V model. The V model basically is a methodology for you to summarize the different parts of ECUs, different parts of domains, and how to define their boundaries, and then they shall be work perfectly once each part is done and now integrated into one vehicle. However, in the past decades, like the auto OEMs find out the SPICE V model is not as powerful as they think. Yeah, because the software now is fast evolving into a brand new world. So all the methodology now is not suitable for the modern vehicle software. Yeah. But AutoSAR and the SOA or SDV's trending is inevitable. So this is also another huge challenge the OEM is facing, and also the challenge we are facing, because we stand with OEMs to deliver the software in the vehicle to the end customers. And the OEMs nowadays, want to pursue the high portfolio and fast product iteration pace, which makes things worse. So we always think that one problem is still remains, but however, a new features, new requirements is to step in. So we always like push us to the envelope, to our limits. Yeah. So as I summarized in the previous slides, yeah, a lot of challenge there, a lot of opportunities lies upon us, but here is how we tackle them. Yeah. So I believe I don't need to do a more introduction of EMQ, but I do need to introduce a little bit our roadmap in the vehicle SDV products. In the previous days, the EMQ was focusing on the TSP part, the TSP telemetric cloud service. But nowadays, we're now moving into the inside of vehicles. In order to provide our customers, the OEMs, a powerful tool chain and powerful in-vehicle data engines to tackle those challenges and to deliver a more convenient SDV features. We build EMQ SDV platform, which is mainly focusing on the data closed loop applications. So since we are in office hour here, and EMQ is a open source company, yeah. So our products here, the platform here, is majorly based on our previous open source products, which is NanoQ and eCyber. Both of them are open source project under Linux Foundation Edge umbrella. And basically, data closed loop is a methodology that describe the whole life cycle of your vehicle data. Yet, your vehicle generates data continuously, and you need to filtering and processing those data in real time. You deploy the data acquisition rules and algorithm here, and those data is collected from other different domains in your vehicles, and those data are being streamed in the real time, very high data volume. Yeah, then we might need to offload some AI computations to DSP to for the hardware accelerations. Yeah, then we transmit this outcome result to the cloud. The clouds shall be capable of sustaining millions of concurrency vehicle connections, and those vehicle connections are pumping data into your cloud engine. Your cloud engine, this part is where our partners Carlinx products lies here. They bridge these data with other third-party features and with other smart features to make this data useful, to find out patterns from this data, like doing offline annotations, or we got a malfunctioning feature in the vehicle. Then we can do a simulation and verification of that features based on those data we collected before. Then we train our new models. Then we update the models. So this is how we provide a closed loop iteration cycle for our customers to make their vehicles better and better. Here is just another picture I just explained. Yeah. So first part of the data closed loop is universal messaging bus. So what I just mentioned in the picture here, yeah, the data type here is pretty fragmented, but we need to converge them in one place. So we need a powerful messaging bus. A powerful messaging bus should be capable of like bridging to some IP, bridging to DDS, bridging to ROS, which the ROS is ecosystem of robotics. Yeah, but it's usually being used for building the prototype of vehicles. Yeah, and bridging to like a CAN bus. Yeah. So this messaging should be can be exchanged in a very high pace, very high performant power, very high performant standards in the messaging in the NanoQ here. So NanoQ is built for you to provide messaging sharing, signal sharing, and even more a streaming engine. A streaming engine means the string storage. So the data in your vehicle, which is generated continuously, but you might not be interested in the data which is generated like last month. So in your vehicle, you actually need the messaging queue here. So we combine, let's just say the Parquet standards. We combine the Parquet format with MQTT and other protocols in the vehicles. Those messaging flows into the messaging bus here, and they being stored in your vehicles. And once an event happens, once it triggers rules, then we can fetch this data back for a further usage. Yeah. So here's another feature showing like how we can be used in modern vehicles. Yeah. So this is how imagine this. This is a different DCU. This part is power chain. This part is DHU. This is BCM. This is ADAS. They each has a sibling ECUs under it. They might have their own isolated CAN bus. So our NanoQ here can be deployed on each ECU or each DCU or VCU here. Then they can forms a flexible network topology, and those network topology can share data with each other, and all this and can without damaging the data itself, without damaging your previous features. Now, so you can keep your previous feature, keep your previous code, just add one new component here to open up a new possibilities to build new SDV softwares. So this is what we gonna see in the future vehicles. A more powerful ZCU zonal controlling unit gonna emerge. It's not so we not only have a domain controller, we have a zonal controller here. Here is a final slides of to explain how this data closed loop would be useful in the real world. So imagine this. So the ADAS features is now widely used. Yeah, we love to enable it. Enable the autopiloting while we are in the daily commute, because the driving is pretty exhausted. Yeah, we would like to preserve our time while we're driving, to communicate, to have a phone call with a family, to have a watch a video, or even to have a chat, even to have a meeting. But the ADAS feature requires a huge amount of data to do simulation, to do training, to produce a model, to have a right choice, to make the right decisions while there is obstacles, or there is a danger case emerges. So this is called a corner case. So, but the corner case only happens in a pretty seldom seen scenarios. Yeah. So how could we identify this corner case and preserve the data of this corner case and transmit them back to your cloud? So for the cloud, or for the AI developers to enhance their models. Yeah. So this is a real problem for ADAS developers. So our tool chain here provides a way to deploy a rule or a trigger here. So this trigger you can is defined by your previous experience, like like here. Your vehicle is driving at 200 miles, which is pretty fast, and now suddenly the driver pressed the brake to, so it means that absolutely there is something bad happens. Then these two conditions combines, so it's just like combines pretty obvious triggers. Yeah, these triggers the streaming engine to fetch data from the messaging bus I just mentioned before. The messaging bus here will fetch data from the packet file and find out those signals and those data related to this case, and push them back to the stream engine and to do a fast real-time calculation and make a data sync to your cloud or preserve data in other a safe flash or safe the safe disk. Yeah, the lost data could be used for online annotation or offline annotations. Yeah, or just or it can be transmitted back to your cloud for verification. Yeah. But if the things going worse, like the car crashed, yeah, which we wouldn't like to see. Yeah. However, like before the car crashed, you only got like 1 to 1.5 seconds for your hardware, for your software to react. How to identify the most precious data in this 1 second is essential. So for this so you can define the rules here, and with our powerful MQTT over quick multi-stream channels, we can put those data with high priorities in front of those other data like heartbeat, like cockpit metrics. Yeah, those high priorities precious data, which is essential for insurance assessment, could be transmitted back in the real time in these 1 to 1.5 seconds. Now, this is how we save life. This is how we make your make accident counts. Yeah, to prevent more accidents to happen. Yeah. Okay, I believe I ran out of slides. Yeah.
Great.
And I'll also run out of time. Sorry.
No worries. Thank you so much for your sharing, Jalen. Really appreciate it. I will. So now we are opening up for Q&A, and I've already seen 2 questions in the Q&A tab. Jalen, Liu, any of you want to pick up those questions? And before you answer, please do repeat the question because most audience can't really see the questions.
You mean a question under the Q&A channel?
Yes.
I see there are 2 questions.
Yes.
Okay, so I'm gonna pick the last one. Is the data transfer real time? What happens if driving in an area without internet connection? Yeah, actually, this is a pretty commonly happen things. While you're driving through a tunnel, yeah, while you're driving across city borders, or then across a different station. So the connection gonna be dropped and reconnect. And I need to please allow me to reshare my screen.
Yeah, sure.
As I just mentioned here, so the connection, unstable connection is a pretty commonly seen case in for automotive for your vehicles, because this is this is mobility. It's not something fixed in your IDC. Yeah, so we got two ways to solve these problems. The first one is so for those short time disconnect, the messaging bus here, yeah. Just take the picture. Yeah, the messaging bus here. It also responsible for bridging data to the cloud. Once it discover the data the connection is dropped, and there's no network available, it will be cache data locally in the memories. Yeah, and once the network is restored, it's gonna auto retransmit those data. And another part is here I say the new protocol called MQTT real quick. Yeah, MQTT quick could help you to overcome those poor networking conditions. Yeah, and we already have a positive feedback from our piloting customers. They use MQTT real quick for like remote driving, for to preserve the high priority data, So the MQTT real quick gonna helps you to ensure the high priority data gets the better bandwidth with the multi-stream. With TCP, you only got one data packet gonna be transmitted at a moment. With MQTT real quick, so it's like a parallel communication. So here's another example here. We have another level 4 autopiloting solution company. They provide the logistic service in the airports. So airports is another typical case with a place which has only have a limited network accessibilities. But with MQTT quick, they can have a better connection. They can running their service at a place where they couldn't before. Okay.
From my side, I will pick the Prakash 2 questions from my side. So the first question is that how to overcome the regional security compliance, especially while traveling. Basically, based on our experience, the OEM usually will inform the user about the scope, the scope of data collection while the user is using the vehicle every time. So from the user side, he or she will be informed that the data will be collected while traveling. This is from the vehicle side. And from the solution side, between the vehicle to cloud connection, the data passing through will be encrypted. Will be encrypted from the vehicle side to make sure the data transmission security. That's how the solution was designed in the Hyperflow. About the second question, should edge computing be placed at the vehicle end or managed in cloud data ingress? I think the answer to this question is so far the solution of Hyperflow is designed like this. So we put the edge computing on the vehicle side because we want to take the full use of the capability of DHU computing, so that we want the results we want is that most of the calculating and results can be directly performed in the DHU and with less reliance on the vehicle side, because we want to make a more active and a more active experience to the users. Because there are some occasions like the bad network may happen in a lot of time. So that's why we designed the solution like this. Hoping my answers can answer your questions. Thank you.
Okay, I see there is a following up questions of that networking issues. So as mentioned, there are tons of data generated every second. How large is the cache that can car can manage? For example, I drive internal for a long time. Is this counted when designing the system? Sure, it should be. And it is one part of ISO standards and one part of one part while we are picking the models of the controllers. One main controller is the flash disk. So the flash disk has different. They are made of different materials, which each flash has central drivers. Those drivers are responsible for writing data, wiping out of data, and to prevent the flash run off their time, prevent the wear out of flash being used to store your data. So we need to calculate lifespan of your flash. We need to calculate how many times we're gonna write for a day or for a month, and how long this vehicle gonna serve in the market, and so combine this map pyramid together. So we basically we need to pick the different hardwares, and basically we need to pick up the to design the different writing frequencies and writing strategies, and for the data catching, for the data storage, and then all this must be considered in our whole situation. Yeah, I see there's a test pops up.
Yeah, I just launched a poll, just like we mentioned in the beginning of the session. We always like to hear people's feedback and know what other subject people want to talk about. If anyone have any questions, we're calling for the last rounds of questions. Feel free to type in the Q&A session. We will give a few 10 seconds if you have a question. Oh, thank you. We're hearing a bit. Thank you from Gokhan. Thank you, Gokhan, for choosing EMQX. We really appreciate your support, and we will continue to improve our product and services. Okay. If there is no more questions or messages, I think that will be mostly for today's session. As always, you can contact EMQ by filling out on our contact us form. And with Carlinx, you can always email them at the following email address on the screen. And we really appreciate you staying with us for so long. And that's it for today's session. We look forward to hear from you and addressing more questions in the next session. Thank you, everyone. See you in the next session.